Hello, AP Calculus students. Mr. Meunier back again for another day of virtual learning. Today, we're going to quickly get through topic 1.8, determining limits using the squeeze theorem. We've been working throughout this course thus far on limits. We started with limits graphically, looking at a picture and finding if the left and the right sides come together. A limit's where you're moving to, not where you're at. We moved on to limits analytically, where ideally you can plug the value into the function to find the limit. Sometimes you get unusual cases with a 0 over a 0 called an indeterminate form, and that requires you to try to factor, cancel, use conjugates, expand, a lot of different tools that we have to pull out from algebra class to simplify those limits that just don't quite want to work the way we want them to. Today, we're going to introduce something new called the squeeze theorem. Squeeze theorem is kind of a common sense idea that caught people off guard on the AP test a couple of years ago because it hadn't really been tested up until that point before. What the squeeze theorem basically says is if you have three functions and we know one function is always, like h of x, is always going to be on bottom. So this h function is always small, underneath, less than. And then you have an f function that's always going to be in the middle. And as you can see on this right-hand side, there's an f, this black line, always in the middle. And a g function that's always going to be on top, or always the largest. So h is always smaller than f, which is always smaller than g. I should say less than or equal to, not smaller than, but less than or equal to f, and then less than or equal to g. If we know those three things are true, and f is maybe an unusual function, but we do know there's a spot where the h limit and the g limit, the bottom limit and the top limit come together, then that middle limit, f, also has to equal it. So again, if we know g and h have the same limit answer, then f also has to be in there. It's going to squeeze together like this picture's doing. H, G, F, and they all squeeze together in this one spot. And that is the squeeze theorem. So what this was typically used for is there's some proofs with some trigonometry that gives us the solution to some unusual limits. It's like the sine of x over x equal to 1. That is unusual because if I plug 0 into this, like we would like to do typically, the sine of 0 over 0 is going to be 0 on top of 0. That's indeterminate. But with the squeeze theorem, with some manipulations, and it's kind of down below this proof piece, I'm not going to work through a whole lot, we can set up a case where we know sine of x over x at 0 is going to equal 1. Or the reciprocal of that, x over sine of x is going to equal 1. And the same thing kind of happens here. As you plug 0 in, ideally, you're going to get 1 minus the cosine of 0 over 0. Well, that's 1 minus 1 over 0, which is 0 over 0. So that's no good. We can't go by that. But with squeeze theorem manipulations, we know this is going to converge on 0. And the same thing with this one, cosine x minus 1 over x does equal 0. Your best bet is to know these. There's not a whole lot of trig in calculus necessarily. It's mainly knowing your values from chart quizzes or unit circle quizzes and kind of knowing these basic limits. Sine x over x is 1. 1 minus cosine x over x is 0. And again, those are developed by taking these area of triangle, area of sectors, area of triangle pieces where we can have one's always big, one's in the middle, one's always little. And if we squeeze them all together, we get the fact that sine x over x is 1. But more importantly for us, How do I use that to simplify some limits that typically would not be simple? Again, if I plug 0 into this off to the side, you're going to get a tangent of 0 over 0. Tangent of 0 is 0, and 0 over 0 doesn't work. So we're not in good shape there. But I know from trigonometry class that tangent is equivalent to sine over cosine. So I have sine over cosine all over x. With some manipulation, dividing fractions means I can multiply by the reciprocal of the denominator. You're going to get sine over cosine times 1 over x. From here, I would like to find that sine over x, because we know sine over x equals 1 from the previous page. Right now it's sine over cosine, but the order in which you multiply two items doesn't matter. So I can switch, flip-flop these denominator pieces in this case, because cosine times x or x times cosine doesn't make a big difference. We get sine of x over x times 1 over cosine of x. Now it goes back to a few days ago when we did multiple problems inside of a limit. If I'm multiplying, dividing, adding, or subtracting things within a limit, I can split that into two limits. So limit x approaches 0 of sine x over x times limit x approaches 0, 1 over cosine of x. And now we're in good shape because sine of x over x, limit as x approaches 0 of sine of x over x, this piece here always equals 1 by that definition, that formula on the previous page. So that's done, times here I can plug 0 in, 1 over cosine of 0. You might have forgotten from trig class, but cosine of 0 is a 1. So that's 1 times 1 over 1, which equals 1 for our solution. All right. So there's that one. Maybe use some trig identities from last year to turn things into the sine x over x form that we're looking for. This one. Sine 4x over x, again, if I plug in 0, I'm going to get a 0 on top of 0, which doesn't work. This is not the form we're looking for. We want sine of x over x. But one thing to pay attention to, in this case, this is a 1x and a 1x. Sine of 1x over 1x. We really just need these to match. The denominator needs to match what's within the sine function itself. I have a 4x inside here, which means I need a 4x in my denominator. We can do that if we multiply by 4 over 4. And that's okay. Again, if you multiply the top and the bottom by a value, that's not illegal because you're multiplying it by 1. We're just going to change the way it looks. So as I rewrite this, we're going to get the limit as x approaches 0 of 4 sine 4x all over 4x. Now we're in good shape because this 4x is matching the 4x underneath. I can split this into two pieces where I have the number 4 as a limit and then the sine 4x over 4x as its own limit where they're multiplied together. Limit x approaches 0 of the number 4 times limit x approaches 0 of sine 4x over 4x. So that's going to give us a 4 for the constant. Sine 4x over 4x is going to give us a 1, and 4 times 1 is 4. All righty. So one more of these. Limit x approaches 0, 1 minus cosine squared x over x. Again, these formulas, that's close, but we're kind of probably going to want 1 minus cosine x over x. What we have is not quite what we're looking for here. And I can't plug in 0 because that's going to give me a 0 on top of a 0. 1 minus cosine squared, though, is factorable. It's a difference of squares. It's kind of like a x squared minus 4 is an x plus 2x minus 2. This is a 1 plus cosine x, 1 minus cosine x, all over x. From here, we're close to what we want. This 1 minus cosine x over x piece kind of works together. That will always equal the 0 value. And I can split this into 2 pieces again. It's multiplied together. Limit 1 plus cosine of x times the limit x approaches 0 of 1 minus cosine x over x. This on the right side is a 0 by definition from the squeeze theorem. Left side, I can plug the 1 in, 1 plus cosine of 0. Cosine of 0 is a 1. So we're going to end up with 1 plus 1 times 0, which is really just going to be 0 overall. And last, non-formula wise, using the squeeze theorem to verify something. First off, we have h of x is negative x squared, f of x is x squared times cosine 10 pi x, and g of x is x squared. We do need a statement on this. It should be here. We should say something like such that to make this work, h of x is less than equal to f of x, less than equal to g of x. That's important. We need that to utilize the squeeze theorem. Basically, the h problem is always going to be the smallest, the g problem is always the largest, the f problem is always in the middle. Use the squeeze theorem to show that the limit x approaches 0 of f of x equals 0. Well, to do that, the f problem is pretty nasty to work with. So we're going to go ahead and do the limit as x approaches 0 of the h problem. I'm also going to do the limit as x approaches 0 of the g problem. So for each of these, as I work these out, the limit as x approaches 0 of negative x squared, if I plug 0 into that, is going to give us 0. And if I plug 0 into positive x squared, I'm going to have 0. So therefore, by squeeze theorem, the limit as x approaches 0 of f of x equals 0. Or we could have another statement maybe down here somewhere that says, that's true since 0 is less than equal to x squared times cosine 10 pi x less than equal to 0 for those answers. That means by the squeeze theorem, the limit as x approaches 0 of f of x has to be 0. So again, we just showed a few things here. We showed the limit for the smallest piece is 0. The limit for the largest piece is 0. We said that the middle piece, x squared cosine 10 pi x, is always going to be between the small and the large. So 0 is less than that, which is less than 0. Therefore, by the squeeze theorem, that limit has to equal 0. So we kind of need to show all of these pieces, the little limit, the big limit, how that fits in the middle of those, and then utilize squeeze theorem to answer the problem. If you graph these, you can clearly see what's going on. I recommend getting your calculator out, plugging these things in. I've done it already. I changed my window. Again, on window, I can go menu, window, window settings, and I typed in physically, I want a -1 to +1 for the x-axis, -1 to +1 for the y-axis. I typed in all three problems, and we can see x squared is always the largest on top. -x squared is always the smallest on bottom. F of x is always in the middle, and it kind of oscillates like crazy going on, and then it expands out. And it makes a nice little picture here that squeezes into 0 at 0. All right, guys, that's all we really had for today. With this, there's a topic 1.8 worksheet in your folder. Look at that. Knock those problems out. The ones I asked you to do in the direction guide, might need to copy on a different piece of paper. And as far as submitting those answers, we're going to finish that out, figure that out later. Make sure you submit your topic 1.6 homework problems in Schoology for me. And that's all we got. I hope you're doing well. If you need help, pop into the Zoom session during your class period. And I'm happy to help clear up any problems you're having, any questions you have. Have a good day.